Welcome to this section on people counting with TensorFlow. This task involves taking in an image like this one and then automatically counting the number of people in this image feed or this image from a video feed, which in this case gives us a total of 54 people. So this means that in this case, our data set is made of inputs, which are this kind of images, and then outputs, which contain this points here. So this like a sample output where we have all the positions in this input image where we have the head of a person found. The data set we shall be working with is the Shanghai tech data set. The Shanghai tech data set is made of two main parts. That's the part A and the part B. And the part A, we have more of very densely packed people in an image, whereas the part B contains images where the people are not very close to each other. So let's look at the part A. Here we have the training and the test data, the ground. We have the images here. So here we have 182 images, ground truth 182. We also have the training, the images 300, and then the ground truth 2. So what happens here is we have this image, for example, this image one right here. You see that these people are, it's kind of like a very densely packed image. And then this ground truth data right here contains all the points in the image where there is a human head. If we enlarge these images, we see we have this kind of very crowded images. So we see that with this data set, we'll be able to train models which could, for example, in the case where we are having a drone during an event, we could count or predict the number of people who are at that event just by taking an aerial photo of the event. So we'll see the kind of images we have here. Now for the part B, we have less crowded images. We could see that they're just footage from CCTV cameras of people moving across the streets and maybe going to buy or going to your various occupations. Unlike with the part A, where we have very huge crowds, showing that people have actually come together for an event. You could get this data set via this link right here. Now once we have this input as an image and then we have this output which shows us exactly where the different persons are found in the image, the first idea that comes to our mind will be maybe to take that input and then train end to end with this output points. But generally in people counting, we don't use this output like this. We actually transform this output into a Gaussian map. Now a Gaussian map looks like this. This here is what we obtain when we have many points. But now if we have just one point, that's just one person, the map we shall obtain will look like this. Now instead for us to focus on just one pixel point where the person's head is found and give the value of 1, what we do is we draw some sort of circle around that person's head where the sum of all the points or the different values we shall give will be equal to 1. So this means that that point with value 1 has been scattered all around that circle such that all those different values will not give the value 1, unlike the previous situation where we have just one point which is of value 1 and all the surroundings of value 0. In this case we have that one point which may take a value of say 0.2, points around 0.1, around 0.05, 0.005, and so on and so forth. But what's important to note is that the sum of all those gives us a value of 1, such that when we have many of them, like in this case, we see that wherever we have so many people, we have this this yellow color here telling us that these circles that we have here have somehow come together. Because if we have, say, let's take these two people here, if we have these two people together, this person's own circle with this other person's own circle will tend to form a region where the values are higher than in the situation where we have these two people who are a bit separate from each other. But in the case where we were using these maps, we wouldn't have this, and that will be because this point will have a value 1, all this point around it will have value 0, this point value 1, everything around it having value 0, this point 1, this point 1, everything around it having value 0. But with the maps, as we could see now, regions surrounding places where there are many people tend to have or tend to take higher values as compared to, say, regions like this one around this two people here. It happens that the way we distribute these points around a person's head follows a Gaussian distribution. Now, although we're using a two-dimensional Gaussian distribution here for the points surrounding the person, we are going to explain this using this 1D Gaussian distribution. This x-axis represents the position of a pixel, and then the y-axis represents the probability of that pixel being ahead. So this means that the closer we are to a given head, the higher the probability score, as we could see right here. This pixel positions which are around the head, which we could consider the head to, or the head position to be the mean. Now this position right here is the mean, and then we also have a standard deviation, which is like a value or a position from the mean above which the probability of being ahead is very, very low. So if our standard deviation is, say, at this point here, so we have there's a mean yet right here, which is considered to be mu. As you can see right here, we have mu minus sigma, mu plus sigma, and we'll notice that above this, like this mu minus sigma, mu plus sigma, if we cut this through the Gaussian bell-shaped curve, we'll see that all values which fall in this range have a reasonable probability of being ahead. But as soon as we move out of the range, this probability becomes very, very small. And that's why we see right here that as we are at this actual point where the person's head is found, we have this very yellow color. As we're going out of this, it turns greenish, and then bluish, and then purple, and then finally gets this purple color. Now note that the very yellow actually stands for 1, and then this purple color stands for 0. But nonetheless, this isn't actually 1, since the 1 value has been shared among all the different points surrounding the person. So yeah, we could have a value of, say, 0.5, and then values surrounding have a value of 0.1, and then 0.05, and so on and so forth. Now, to get the details of the Gaussian distribution, you can look at our course on probability. Now, we are going to be generating this kind of maps for each of the points. Now, let's look at the formula for this probability distribution right here. This probability distribution is defined such that we have P of x, where x is the position, is equals 1 divided by the square root of 2 pi sigma square, where sigma is the standard deviation. Now, note that the standard deviation can be defined such that this region within which we have this reasonable probability score of being ahead, of being a person, is restrained to only positions which are very close to the person's head. So in that sense, this mu minus sigma now falls around this, and mu plus sigma falls around this position right here. And from this, we see clearly that this is going to be a hyperparameter for our model, wherein we could vary the values for this sigma to see whether, when we choose points, or when we decide to work with points very close to the person's head, or we decide to work with points which are also very far from the person's head, that's generating maps such that this circle is very large. We see how it affects our model's accuracy in predicting whether there is a person in that position or not, or better still, in counting the number of people who are located in that image. So that said, the standard deviation, as the word goes, is a deviation. So it tells us how much, or better still, how many points surrounding the head we decide to share that one score of the head with. So here we have this. Now this is what we get here, times e to the negative half of x minus mu. Mu is the mean, divided by sigma, all of that squared. We are gonna consider the mu to be equal to 0. So this is gonna be minus half of x divided by sigma, all of that squared. And since the Gaussian distribution is a probability distribution, more specifically a continuous probability distribution, the integral from negative infinity to positive infinity of p of x dx is equals 1. Now this comes back to the fact that we are having a point here at the center which we are sharing across all these different points surrounding it, and that's why when you find that integral here, we have a value of 1. Now recall, this integral is just like finding the area under this curve right here. So you see this shaded portion in orange here. This area should always be equals 1. And then coming back to the image, this comes to the fact that the sum of all these different pixel values surrounding this head should be equals 1. And that said, when we have so many different positions like this, if we sum all the pixel values, they should all give us values of 1.